Thank you. Thanks very much for the intro, and also thanks for the invitation, both Ricardo and Andrea, for this. So I'm part of this machine listening lab, which is a relatively new lab, and there are also a few members of this lab here as well, which is about signal processing and machine learning methods for analyzing sounds, analyzing audio recordings. You can view the website for any more information. If you think your interests are aligned with this lab, please just send an email and join us. So today I'm going to talk about machine listening, so computational methods for analyzing sounds and extracting meaning from sounds. And particularly I'm going to talk about my research in matrix decomposition methods for analyzing audio recordings and how these can be applied to both music recordings and analyzing everyday sounds. So about machine listening is basically it's the discipline of extracting meaningful information from audio signals. And when we're talking about audio signals, it can be pretty much everything. It can be speech, it can be environmental sounds from nature or from city soundscapes. It can be music recordings, which is kind of a big thing here at Queen Mary. And it involves a few disciplines. First of all, signal processing, but also increasingly so machine learning. And also there are quite a few elements from acoustics and also from perception, cognition, and then if we delve into specific problems, then we come up, for example, if we're talking about music, then we have some input from musicology. If we are talking about speech, then we have linguistics and so on. And the whole process is basically that you assume access to some sort of audio recording and you want to transform it to extract some information, and in the end to maybe separate this recording into its basic components, into speech, into the music part, into the environmental sound part, and to identify each and every source and everything that happens in the signal. That's the whole idea behind machine listening. As far as music is concerned, the big problem right now is in machine listening is to convert a music recording into some sort of notation where you can understand what's happening inside. So you can identify things like notes, you can identify instruments, you can understand what's the rhythm there. And this sort of analysis has applications in many areas, most of which are sort of represented at the Center for Digital Music of the School of X. So the first and foremost is music information retrieval, so how to retrieve information from music content. Also interactive music systems, for example, if you want to create some sort of system that can do automatic accompaniment, computer music, or musicology, and many more. And when we switch now to the everyday sounds part, this is an emerging topic in the field of audio signal processing, the analysis of sort of everyday sound scenes. And a few core problems have been identified. First of all, to detect sounds. So right now, what you hear is probably just me talking, maybe some sort of air conditioning in the back, so the specific events happening. Sound recognition, so to also automatically come up with systems that can understand the environment of a recording. So was this recording made in an office? Was it made in a street, in a park? These sort of things. And also to separate the sources, so source separation. And there are quite a lot of applications, and actually new applications come every day for audio archiving, so how to sort of intelligently analyze and index, organize audio sound collections. Also security surveillance, for example, if you can come up with a system that can automatically detect gunshots or glass breaking in a house scenario, something like that, or baby cries. So it also has then applications for smart homes, so to come up with applications that sort of can be used for embedded assisted living, or as sort of, for example, you might have seen, I don't know how many of you received yesterday an email from Amazon talking about the new Amazon Echo, which is finally available in the UK, which is kind of like this sort of smart device where you put somewhere in your home and then you talk to it and you can sort of follow your orders and order stuff or whatever. And another area which is also prominent in the School of X is acoustic ecology, so how to use these sort of auditory monitoring applications, auditory sensing applications for understanding what's happening in nature, so for example for biodiversity assessment applications. And when we're talking about, for example, sound event detection, what we see is something resembling this. So this here is a spectrogram of a sound recording. This is The vertical axis is frequency, and the horizontal is time. And in sound event detection, we want to identify specific events that happen within an audio recording. This one is from an office sound scene where we have things like door knocks, people turning pages, keyboard clicks, and things like that. So where does matrix factorization come into this? So many of you might be familiar with this method called NMF, standing for non-negative matrix factorization. It's a technique, an unsupervised method for factorizing a matrix into a low-rank decomposition. Essentially, it means to take as input a matrix and come up with two other matrices. And the constraint is non-negative data. It originated from the field of image processing, where there were a few researchers, Lee and Sung, who wanted to come up with a system that could decompose faces into their constituent parts. Let's say that a face is basically a linear combination of basic elements, such as the nose, the eyes, the mouth, etc. That was the idea. But ever since, this sort of main algorithm has grown for many applications in machine learning for detecting pattern recognition, dimensionality reduction, clustering, and so on. And the basic model is that you have as input some sort of non-negative matrix B. It could be an image, it could be an audio spectrogram, it could be a bag of words representation in text documents. And the idea is to come up with some sort of factorization to approximate the input into two matrices W and H, all of which are non-negative. And the idea is that the rank of this decomposition, so the dimensions of this W and H, are smaller, so we can compress the data into something meaningful. And many algorithms have been proposed in order to come up with this sort of factorization over the past 15 years or so. So how can this thing be applied to audio? Let's assume that we have as input an audio spectrum. This is a spectrum of a music recording, which I'm going to play now. I don't know if you understand what's happening. So we have one note here, another note entering here, another note here, another note. Some of these are overlapping over time as well. This magnitude spectrum is also a non-negative matrix in a way. So if we apply NMF to this thing, then we can come up with these two sets of matrices. This is our W matrix, and this is our H matrix. And perhaps surprisingly, people found out that this W matrix stores sort of fingerprints of every sort of acoustic event happening in the audio. Sort of every discrete note which was played in the audio is there. Sort of this might be C, this might be note D, and so on and so on. And this matrix here also, perhaps surprisingly, stored information of which note was active at a given time. So which acoustic event, which audio event was active at a specific moment in time. So we can use that kind of output to come up with sort of a machine listening sort of application in the end. More or less at the same time, in the field of text retrieval and text processing, there was this person, Thomas Hoffman, who came up with this technique which he called probabilistic latent semantic indexing, PLSI, which was then adopted by the video processing community, and they renamed it as probabilistic latent semantic analysis, PLSA. Some of you might be familiar with it. And it had been used, for example, for tagging video recordings for human action recognition and this sort of stuff. And then it was also incorporated by the audio people, and they rebranded it as probabilistic latent component analysis, PLCA. In fact, all these PLSI, PLCA methods are essentially probabilistic counterparts of this non-negative matrix factorization method, but it's actually sort of the same method, but from a probabilistic perspective, where the model is a bit more flexible, and we can plug in some other models from probabilistic machine learning theory and come up with more interesting stuff. So this is how the PLCA model looks like. So this is the same thing as the NMF model I showed you before, but this is sort of expressed with probabilities. The idea is that we have as input a matrix, in this case a spectrogram of frequency and time, and in this model it's approximated as a bivariate distribution of frequency and time, which is in turn decomposed into two sets of matrices essentially, or two probabilities. One is the probability of a frequency given a specific component or acoustic event, so this is our W matrix. And the other part is what's the probability of a component being active at a specific time frame. So this is our H matrix. This is the main output we want to get. So essentially this model can decompose a spectrogram into, firstly, spectral bases and also event activation. So it tells us when each sound is present at a given time instant. So this basic model has been used for the past maybe 10 years or so for various applications in audio processing, machine listening, for detecting sounds, for detecting notes, for also it can be used for source separation or source identification as well. So for example, in music we can use it to identify instruments, or in speech we can use it to separate speakers if we have many people talking at the same time, things like that. People also came up with interesting extensions of these things. I want to get into detail about this equation here, but the main goal is that we can use it also, we can come up with convoluted models. The previous one was a linear model, so it was basically a matrix multiplication. This one here is a convolution, so you can actually use it to extract shifted structures out of non-negative data. So for example, imagine that you have a picture like this where you have many faces in the picture and you want to extract a sort of prototype faces out of each one. So this is kind of like a shift invariant approach to extract data. And this also has been used in music in the context of using as input representations in the log frequency, where they have some nice properties about music, in the sense that if we shift a pattern vertically across a log frequency spectrogram, we can also extract information about tuning and pitch. We can also come up with this two-dimensional convoluted models, which basically can extract two-dimensional patches from a bigger spectrogram. So this is essentially extracting smaller images out of a bigger image. In this case here, we have a spectrogram of some footsteps, which I'm going to play now. So we had 4 footsteps. I guess 2 from a left foot, 2 from the right foot, or vice versa. And if we apply this convolutive NMF method using square patches, and then we can extract 2 sort of fingerprints, 1 for each foot, and then we can also come up with some sort of activation which tells us which foot was active at a given time frame. So we have these spikes here which correspond to the left foot, and these spikes that correspond to the right foot. So we can actually extract some information about what happened in the audio signal. So how can these things be applied to, firstly, to music signal analysis? So part of my work over the years, the past few years, has been to create a system for music transcription, so a system that can automatically detect notes in music. And to use this convolutive property to also come up with, to explain things like tuning changes, and also to come up with some sort of temporal constraints to explain how a note evolves over time. So here, for example, you see this is a spectrogram of a piano note, which I'm going to play now. Sorry. As you might hear, the note sort of changes over time. I'm going to play it again. It's not the same when it started and when it's finished. Something has changed. So this can be expressed as a succession, as a temporal succession of spectral fingerprints or spectral templates. So that was one of the concepts behind this work. And the bigger picture basically was to come up with a system that can take as input an audio recording, compute a spectrogram, and then fit it into one of these matrix factorization models, which would use as side information a dictionary, a big dictionary of many different instruments over many notes, and to come up in the end with some sort of representation that tells us which notes were active. So in my case, this was a MIDI file. And this is how the system worked so far. So I'm going to play now a recording, I think, from a Mozart piano sonata. And on the top here, you can see the sort of a ground truth of which note. So the note index is on the vertical axis, the horizontal axis is time, which note is active at a given time frame. And below you see the output of the system, so it can detect multiple concurrent notes over time. I'm going to play now a synthesis of the output. So as you might hear, the system was mostly correct. It did miss a few notes, but most of the content of the music recording was there. And because of this convolutive property, we can also do some interesting stuff about tracking sort of tiny changes in frequency and tuning. So this is a recording from violins, and so it's actually a string quartet. And if you might be able to see, so there's tiny fluctuations here which represent sort of the slight frequency modulations that are produced by sort of these instruments that can do vibrati and things like that. So we can use it for some sort of more high level and detailed analysis of the music. And about the speed, so in the end the system is fairly fast. So in my old 4-year-old laptop, I can have up to 1 times real-time implementation using just MATLAB, but also can considerably speed things up using GPU computing. So the good thing about NMF and these kinds of models is that it's all matrix multiplications. And matrix multiplications can be pretty much optimized using GPU computing techniques. I also submitted the system to this annual competition we have in the music informatics community. This might be similar, for example, to the track fit competitions in video processing. And it ranked first in 2 years. And code for the system is also available in the website there below. We also continued this work with Siddharth Siktia, who's a finishing PhD student here at EECS. Siddharth is I don't know if you know him, he's one of the local deep learning experts. And we were very keen on using deep networks in order to model music signals on the one hand, but also to use them as language models for music. So the motivation was basically that if you have a system for automatic speech recognition, for example, the systems that can be found in Google or in the Siri systems, all these consist of 2 components. One is the acoustic component, which basically is a system that tries to understand what's happening in the audio. And the other component is a language model, which tries to sort of use some sort of probabilities to say that, okay, if you said this word, what's the probability that you'll say the next word then? Something like that. So the idea was to enhance the transcription system for music with some sort of language model so that we would understand. So if we have some sort of note pattern at one time frame, what's going to be the probability that we have the next note pattern in the next time frame? So to do some sort of music prediction. And it was shown that the system, this deep network-based system that was using recurrent neural networks can significantly improve transcription performance. There's also, through the efforts of Chris Cunningham, who's the local software developer at the Center for Digital Music, there is also a VAMP plugin, which is one of the plugins circulated through the Center for Digital Music, and it can be used, this transcription system can be used to analyze music recordings through the Sonic Visualizer software, which is probably the most famous piece of software being developed at the group. So moving on now to the other part of my presentation, which is sound scene analysis. So how to use these matrix factorization methods to extract information from everyday sounds. So the idea here, I was working in an office scenario. So basically I had office recordings. Most of these recordings were actually recorded in the engineering building here. And the idea was that I wanted to detect all events that were happening there. So things like people coughing, keyboards, mouse clicks, doors opening and closing, all that kind of stuff. And so the motivation was to come up with a system that could detect office sounds, and in order to do that, I adapted one of these PLC models, where each of these sound classes was a dictionary of several exemplars, so sort of example sounds, let's say. And each of these example sounds, let's say a door knock or someone clearing a throat, consists of a sequence of sound states, so basically a succession of things that happen within an audio event. And the motivation was to finally to control the succession of these sound states using hidden Markov models. So basically to combine this spectrum factorization model using PLCA with some sort of temporal constraints using hidden Markov models. That was the idea. And as input in this case, I used a particular flavor of a spectrogram called an equivalent rectangular bandwidth filter bank, ERB spectrogram, which is kind of like auditory motivated in the sense that it corresponds to the way, or at least theoretically, the way that humans perceive sound. And I came up with this model where I tried to decompose one of these spectrograms, again, as a bivariate probability distribution of frequency and time, which is in turn decomposed into a big dictionary, which is a 4-dimensional tensor of frequency, omega, of sound index S, of this is my index of exemplars, and then we have the sound states. So it's a 4-dimensional tensor, and the main output of this system is this probability of viewing a specific event class at a specific time frame. So this tells us which sound was present at a given time. And we also have a few auxiliary probabilities that further constrain the model. So essentially, we have as input a spectrogram, we have a pre-extracted dictionary here, and we want to compute these 3 probabilities there. And the main output is this probability of a sound event over time. And this is how the output looks like. So it's fairly fuzzy. See, this looks like a posterogram for various classes. So in this case, I had 16 classes over time, and this is kind of like the probability of encountering a specific class over time. I also did some post-processing in order to come up with some sort of binarized version to come up with a final list. So telling that definitely, yes, this sound was present at this time frame. And this was applied to this DK's data set. So DK stands for Detection and Classification of Acoustic Scenes and Events. It's a fairly new competition that was that originated from Queen Mary. Mark Plumbley, I don't know if everyone has met him, was the originator of this competition. And the data set sounds something like this. So it's basically a mixture of various sounds recorded mostly at the engineering building and computer science buildings of Queen Mary. And a final application I wanted to also mention was that this matrix factorization model, I tried to also adapt it to identify bird species from continuous recordings. So this sounded a bit like this. So it was as an effort to sort of demonstrate the impact of these kinds of methods in various fields. And I tried to apply this method to another competition that was happening a few years back as part of the ICML workshop. And this was just a very basic PLCA model without any interesting constraints, and the method was competing against various types of multi-layer neural networks and all that kind of stuff. But even so, this simple method was managed to rank on the 25 top % of the submissions. So it shows that these kinds of approaches can learn something meaningful from the sound, because we are sort of we're not constructing a blind model, but we're actually putting quite a lot of sort of prior knowledge within the model and putting a lot of constraints within the model in order to come up with a meaningful solution. So as to sum up, in my opinion at least, these matrix decomposition or matrix factorization methods are powerful tools that can be used for audio analysis and beyond that. And the reason being is that, first of all, they also offer an interpretable sort of output and an interpretable system, so you can understand what's happening inside the system. It's not like a black box. They can also be extended. So I took the basic PLCA model and I added probability, I added constraints, and came up with something which was much more meaningful. They're also computationally efficient in the sense that it's mostly matrix multiplications, and we can come up with systems that work faster than real time. And there are also many other uses that I didn't go through at this presentation, for example, on using these methods for recognizing the environment of a sound recording. Or it can be used for other types of music transcription tasks, or for example for transcribing drums, for recognizing instruments, and so on. And already they are used in several commercial and public tools. This tool here is the part of the Digital Music Lab system that was built in collaboration with the British Library. This is online, and it's using all these NMF-based techniques to analyze recordings from the British Library Sound Archive. I think so far the system has incorporated more than 300,000 recordings and counting. And this system is basically able to visualize the outputs of these NMF-based outputs. And as a future for this field, I think there's quite a lot of research still to do on what's the input to these algorithms. So right now we're using standard spectrograms, but they also can be used a bit more interesting representations, maybe representations that more closely match the way that humans are able to hear. For example, I think there's some research showing that humans are sort of hearing in a three-dimensional sort of way, in the sense that we don't sort of observe sound as a spectrum, as a representation of frequency in time, but we also experience sound at multiple scales, at multiple time scales, so we can maybe incorporate that as well. Another thing we can do for systems that can detect everyday sounds in sort of everyday home or city applications, we can also come with language models, so that, for example, that can understand what's the sort of pattern of sounds happening. So if you, for example, have a microphone in the street, then you can expect some sort of frequency in cars passing, in people passing by, footsteps, this sort of thing. We also need to come up with some taxonomy of sound events, because right now there's no such thing, no predefined taxonomy. Every person who's doing a paper on this topic is coming up with their own sort of class list, and so there's no consensus on that. And a final thing is that we need to also come up with algorithms that can adapt to different environments, and also different devices. So one of the big problems, there's this company called Audio Analytics, some of you might be familiar with it, which is about coming up with technologies for sound recognition in everyday applications. One of the big problems they have is that when the device changes, so if you make a recording using a perfect expensive microphone, that's fine, but then if you make another recording using a smartphone, then the sound changes drastically. And you have to come up with systems that can adapt to this sort of challenges. And that's it. Thanks very much for listening, and thanks also to all these people with whom I collaborated on this work. Thanks very much.